Still me. Kim's coming, I promise. Lesson 7B. Here's the other model we'll work with exclusively in this class, or I should say often. Here's the example. Haagen-Dazs ice cream. 15 Haagen-Dazs ice cream varieties were researched on the internet. Fat grams were graphed, plotted against calories. A dietitian was interested in creating a model to predict calorie count based on fat grams. So clearly, if an ice cream has more fat grams per serving, we would expect it to have more calories. Probably not a perfect relationship. Okay, here's some of the data. I just put this so we can see it. Vanilla, Swiss vanilla, rum raisin, etc. Fat grams versus calories. So vanilla per serving, 18 fat grams and 270 calories. Probably get, what, 1 cup of ice cream for that. Here's the graph. It's a scatter plot. We've probably seen a few scatter plots in class. One variable goes on the x-axis. We're using fat to predict calories. So we'll put fat on the x-axis, calories on the y-axis. After this lesson 7 video, we'll be working with scatter plots and the relationships between two variables for a good 2 weeks, maybe 3. So we'll go quickly here and then we'll get into the details shortly. I look at this picture. There's a clear relationship. As fat grams increase, I move left to right across the graph. Clearly, we have more and more calories per serving. It's not perfect, but I see the relationship. It looks linear. It looks pretty strong, and if I put a line right through this, and I think I will, because, well, it's coming, but I'll put it anyways. I'll just have to erase it. Oh, we're seeing this relationship. Again, to be clear, this straight line, we can think of it as a model compared to the data points, and what we're trying to do is generalize the relationship. We're trying to generalize the relationship between x and y, fat grams, and calories. That straight line is certainly not perfect. I don't even think I hit any of the points, but most of the points are pretty darn close to the line. And so if we can come up with the equation of this line, then we can get to where we want to go. We want to do predictions, right? We want to understand the relationship between the two variables. All right. Again, well, here it is. I guess I put it back in there. The model won't be perfect. The model won't be perfect because, well, almost every point, or I guess I hit one this time, but most every point is not going to fall on the line. But the model still should be useful for predictions, useful for understanding the relationship between the variables. Okay? Now keep in mind, students, I just took a random sample of 15 Haagen-Dazs flavors. I bet there's more than, 15 flavors. If I took another random sample and took different ice creams, I would get different data points. And if I got different data points, then that straight line might shift a little bit, right? The slope might change or the positioning. So we have to keep that in mind, that this line here is going to be our best guess of the true relationship, and it's based on the data that we have collected. Right. So probably will need that line again, but let's see what's on this next slide. All right. Here's the scatter plot. I guess we're going to flip the page in the notes. That's the best linear equation plotted along with the data. You can see it in your notes pretty clear. It's in pink here. I'm not sure if it's coming up in the video, but we're almost there, right? Lesson 9, we come up with how do we obtain this, quote, best line. How do we obtain this best line, question mark. It's coming, I guess we're in lesson 7. It's important. I've always thought to myself, if there's one technique that you learn in Math 127 that you might carry forward to other classes or your careers, linear regression might be that topic. Okay, it comes up often all walks of life. Okay, so there's some questions at the bottom there. Let's get those answered. Part A, what might the dietitian predict for calorie count? Dietitian would like to know calories if a new flavor of ice cream has 15 grams of fat. Okay, so at this point, I don't have the mathematical formula, the y equals mx plus b, you might be familiar from algebra class, to precisely answer this question. So since this is the intro video, let's just eyeball it. 15 grams of fat, smack in the middle of 14 and 16. If I sort of go straight up to the line, there's 15 grams of fat. And if I go straight over, it's probably about in there somewhere. And best guess at this point would be what? 255 calories. This is the eyeball method. We won't use the eyeball method. We'll have the equation. We'll get the precise answer going forward. But for this video, the eyeball method is going to do the job. It'd be helpful probably put that line in there too. Okay? And I could do the same thing. 19. We're going to have 19 grams of fat. Or we find one on the internet. What would the prediction be? I could go straight up to the line, straight across, and do that eyeball prediction. Part B then. What the heck is part B? Something to think about. Should we use this model to predict the calorie count for a new fat-free ice cream? How many grams of fat would a fat-free ice cream have? Fat-free, this is going to be x equals 0 grams of fat. Think about this, and this is important going forward. I built this equation based on the data. Where do I have data? In terms of x, in terms of fat, the least amount of fat in any of these ice creams is about what, 13 grams? Up to what, 23, 22, 23 grams of fat? Because we only have data from about 13 grams of fat up to about 22, 23. We really should not be going to 0 grams of fat. I don't know if this equation would continue down off the board, below onto the wall here, and finally as I moved left, and I don't know if the camera's following me, but somewhere over here is 0, and that diagonal line is going to be about down on the floor. Do we feel comfortable being down here predicting calories? Probably not, right? So it's outside the scope of the model. We've got some space to write here. Let's see here. X equals 0 grams of fat is sort of outside the scope of the data. The data that we've collected is so important. And we only want to make predictions for where we have data. So should we use this model to predict calories? The answer is no. Big, fat, no. The reason here, because that x equals 0 is so far out of the scope of the data. All right, that's it for that slide. Couple minor points to wrap this one up. And let's clean this up. Sometimes I'm wondering what I'm thinking when I have all these fill-in-the-blankers and brand new material. In Math 127, one model that will primarily study for one variable at a time is that normal model. Okay, so that was one video ago. One model will primarily study for one quantitative variable is normal. And remember, that's that bell-shaped curve from the IQ example. How do we know when a normal model will be appropriate? Number one, we must be sure to graph our data first. Graph it to see if it looks normal. It's as simple as that. Be sure to graph the data first. We'd use a histogram, of course, before deciding to use that model. If the data does not look unimodal and symmetric, then try something else. Normal model won't apply. Okay, so a little review from the previous video. We're going to skip this. We're going to do regression first. That's the linear model. Then we'll come back to this, in about a month, maybe 3 weeks. When looking at two variables and how they're related to each other, so looking at the relationship between two quantitative variables, a linear model is often the right choice. Here's a picture. It's not in the notes, but should show up on the video. I've got some data. Who knows even what this is? Quarterly change in unemployment rate versus quarterly change in GDP. The points are well summarized by that straight line coming here with negative slope. So again, you're going to want a graph. Again, we'll first graph our data. The right graph is called a scatter plot. And before we fit a linear model or a linear equation, we better check to see that the relationship is linear, right? Check that it's straight and reasonably strong. Just because we know about normal models and we know about linear models does not mean everything's normal and everything's linear. Always graph, 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 graph. So at the bottom, keep in mind, you have to remember what a model is. It's a generalization of the real world based on that data that we've just happened to collect, right? Maybe we ran an experiment. Maybe we collected some survey data, took a random sample, or possibly just found some information on the internet, right? And whatever data we find, we can base the models on that data. But if we took another sample, the data would change and possibly our model would change as well. So these are just generalizations. We'd like to put some faith in them, but at times we cannot put all the faith in them. It's just a model. To wrap this up, one point I thought of, I'd throw this in this little lecture here. Not all data can be successfully modeled. In Stat 1, MAT127, we're sort of hoping for nice data. Nice normal data, nice linear data. So I found this. This comes from that general survey on StatCrunch 2008. This is highest year of school. And if you look at this, you can see the picture in your notes. I have a big pileup of data right around 12 years of school. Those are the people that finished high school. I have another pileup right around 16 years. That's probably bachelor's degree. I have another little pileup here around 18. Sounds like a master's. Even a little pileup down for the PhDs, but they're dwindling. We don't want to start doing this. Right? Some crazy... There is a math function that looks like that, but we don't want to really go there. So if we see very unusual data, we might not be able to successfully model it, at least in Math 127. So we're looking for those nice patterns. We'll keep it easy in the first course. Right? One other example of that, and I see my stop sign, so this is the last slide. Not all data can be successfully modeled. Here on the right, we surveyed Cecil students back in 2013. We're looking at the relationship. Age, how old are you versus how many Facebook friends do you have? And at Cecil College, most students are 18, 19, 20, and would have a pileup of data in the younger ages. And there are a few students in their 30s and a few students in their 40s and 50s and even 60s. Looking at number of Facebook friends versus age, the data are sort of all over the place. There's not a clear linear pattern. What I don't want you to start inventing is, oh, I can just do that with this data. I don't think that summarizes the trend. That You know, if you're 20, you're guaranteed to have thousands of Facebook friends, and anywhere past 25, you basically have no Facebook friends. We know this is not the case. So always think of the context of the data, always think of what the data is trying to tell you. And certainly you would not look at this and say, well, I'll fit a straight line because I know how to fit a straight line. We don't want to do that as well. All right, so that wraps up this quick lesson. We'll get started with linear regression. It's going to be 3 weeks of fun, so we'll see you in class.